So this lesson is going to start off kind of in a different direction, but we are going to bring it back towards what we're learning this unit. So we're going to start out and just talk about what math is. So some people say, and there's different definitions of what math is as a whole, that math is, in its essence, the science of patterns. So throughout the year so far, we've been talking about patterns, like how do I distribute? What are the properties I have? We just recently finished factoring, using the zero product property to solve equations. So the two main branches of math you've learned about so far are geometry and algebra. So geometry is the branch of mathematics concerned with the properties and relations of points, lines, surfaces, solids, and higher dimension extensions. So when we talk about this idea of math being patterns, some of the patterns that we explore in geometry, we talk about congruence of triangles, right? Whenever we have a side angle side pattern, if you remember from last year, we talk about how all rectangles, no matter how big they are, have diagonals that are congruent. That's another pattern that we can see in all shapes that are rectangles. We also talk about the relationship between the circumference of a circle to its diameter, and we talk about how that's constant. So no matter how big or small I make a circle, if I make a fraction out of the circumference over the diameter, we're always going to get the same thing, and that same thing happens to be pi. When we start to draw pictures, this one I'm not sure if you'll remember as much. If I make a central angle on a circle, which looks like this, that's always twice as big as the inscribed angle that opens up to the same arc. So that's another pattern we find in geometry. Algebra, a different branch of mathematics, is kind of interested in different types of patterns than geometry. So algebra is the part of mathematics in which letters and other general symbols are used to represent numbers and quantities in formulas and equations. So when I think about algebraic patterns, I decided to express it this way, where I just have these variables a, b, c, and x. So for example, one of the patterns we've used recently is that if I have an expression in the form a squared minus b squared, that's equivalent to a plus b times a minus b. We use that for factoring. If I have an equation like this and I want to solve for x, no matter what the values of a, b, and c are, if I move things around, basically I would subtract b and divide by a, so x is always equal to this, and then I could plug actual numbers into it. Another super common pattern, if I have something and I add it to the same thing, I have two of that thing, x plus x is 2x. And then here's an exponential pattern in algebra, where if I'm multiplying, I can add the exponents. So we have to go back pretty far, 500 or 600 years ago, and then before that, thousands of years. Geometry, I would say, is probably a little bit older than algebra in terms of people thinking about shapes before we had to start to think about variables. But for thousands of years, these two fields of math were pretty separate. And even the way we teach them now in high school, you have a year of geometry and a year of algebra. And basically, they did stay separate. We did things with variables. We did things with shapes. Until someone named René Descartes, and I put or Pierre Fermat because basically there's some disagreement about who actually did this, but both of them were kind of involved in inventing the coordinate plane and the resulting field of analytic geometry. So what this meant was we started to take geometric things and we started to do algebra with them. So sorry, I'm just trying to get the page to move down, but I'm pushing the wrong button. So in analytic geometry, and you did some analytic geometry last year, even though maybe you don't know that's what it's called, geometric figures on the coordinate plane, points have locations represented by algebraic variables x and y. So in geometry, we talk about points. Points are a location in space. But then when we have the coordinate plane, we can put a point somewhere, and then we can say where it is with a variable x and y. So in this case, right, we have a point at 4, 2. So it started to bring numbers or variables to this thing that was geometric, which was a point. Once we had points on the coordinate plane, we could express the slope of a line. So lines are another huge part of geometry, right, as an algebraic formula. y2 minus y1 over x2 minus x1. The distance between 2 points. So in geometry, we talk about distances between points. Before analytic geometry, they were just kind of like out there in space. Now we can put them on a graph, and we also have formulas for distance and also midpoint, and those can be represented as algebraic patterns. So it's kind of hard to think of things any other way, because when you learn about geometry, you know, you put things on the coordinate plane, and when we do algebra, we always graph things, right? So, but at one point, it was just algebra with variables, no graphs, because graphs are the coordinate plane, and then there was geometry figures not drawn on the coordinate plane. So it says it's hard to think of it any other way, just like it's hard to imagine the world before modern technology. It was a major paradigm shift. So more importantly for this course, I just kind of mentioned it, the invention of the coordinate plane enables us to see the shapes of algebra. So in algebra, we work with expressions. In different situations, we simplify them, we factor them, we set them equal to each other, etc. So those first 4 lessons where I was just factoring, that was pure algebra. I didn't talk about the graphs of those things, I just worked with them and I manipulated symbols. So now we're going to consider an algebraic expression, 3x plus 1. So 3x plus 1 by itself is pure algebra. 3 times something plus 1. But once we start to talk about it as a function, we're heading towards the coordinate plane, and we can think of this algebraic thing, 3x plus 1, this algebraic expression, as something geometric. So when I ask what's the shape of 3x plus 1, that's something they couldn't even really talk about for a really long time. But if I graph it, I know that 3x plus 1, and I can do this, I'm going to use mx plus b because we know that's what we use, but we could just make a table of values, all the different points where I plug in a number, like I plug in 0 right here to 3x plus 1, and I get 3 times 0 plus 1 is 1, so the point 0, 1's on that graph. So the coordinate plane lets me see that the shape of 3x plus 1 is a line. Another thing we talk about, 3x plus 1 by itself, it's silly to talk about the height of 3x plus 1. But once we have the coordinate plane, we can, and height is a geometry word. So what is the height of 3x plus 1 when x is 3? So I can go over here and go up, okay? And I can see the height here. And when we talk about height on the coordinate plane, we're talking about how far above the x-axis. The height is 10. Now we even have a variable for that height, y, right? So y tells us the height of a graph at a certain x value. What's the height of 3x plus 1 when it crosses the y-axis? So that height is 1. And then what's the slope of 3x plus 1? So we can look at these patterns. Slope is a geometric thing, but we can talk about the geometry of algebra. So this is up 3 over 1, right? We can tell that because we know things about linear equations as well, so the slope is 3. I can write an equation of a parallel line. So parallel lines are another geometric topic, and we're talking about something, parallelism now in algebra, which didn't used to be there. So I'm just going to write for mine y equals 3x minus 5. So even though I'm starting down here at 2, 4, negative 5, if I was going to graph that line, right, I'm creating a line that is parallel to the one that I already have. And sorry, this is hard to draw really nice, so a little bit hard to tell, but you guys get the idea, okay? So next question, I'm going to erase some of the stuff I have. And specifically, I'm going to erase this line because I want to talk about this next question. So it says, if you were to create a shape between the y-axis, the x-axis, 3x plus 1, and the line x equals 3. So let me just draw that in. So here we got the x-axis, here we got the y-axis, and x plus 3. So basically I'm talking about this shape that's created here, okay? What would its area be? So here's a really geometric term, area, correct? And now we're talking about it with algebra, right? So we can actually talk about area now for something that's algebraic, completely separate at one point. So if I look at this, there's a couple different ways I could figure it out. I could split it up into different shapes, so maybe I'll do it that way. So I have a bottom shape here that looks like it's 1 times 3 is 3 for the area, right? Base times height. And then I have a nice little triangle here, and there's different ways we can do this. And there's even a way that we can do it to work for all shapes. So this has a base of 3, and I think the height is 2, 4, 6, 2, 4, 6, 8, 10. It really should intersect here, okay? So this is 9 tall, okay, and 3 across. So 1/2, because it's a triangle, 9 times 3 is 13.5. So this whole shape has an area of 16.5 units squared. So these questions about, and this should say 3x plus 1, I changed the equation and forgot to change it here, all have geometric concepts in them. Their questions were not asked for thousands of years until 3x plus 1 could be viewed as a geometric figure. So looking down the page to kind of summarize this, now we talk about these expressions that just have an x to the first, as the linear family. Their parent function, which basically means, think of it like the parent that everything else came from. The most simple linear function is y equals x. Its shape is a line, thus the name linear. And how to tell if a function will be a line, basically you can write it in y equals something x plus something form. Okay, so y equals mx plus b form. My parent function is an example of that, and that's where the m is 1 and the b is 0. Okay.